Good morning, everyone. It's lovely to see you all here today at our Wednesday public talk. My name is Mitchell Bomer, and it's my pleasure to chair the talk today. Just give people a second to come in and sit down. But before I go on, I would like to make an acknowledgement of this lovely country on which we are meeting here today. Geoscience Australia acknowledges the traditional owners and custodians of country throughout Australia and acknowledges their continuing connection to land, waters, sky and community. We pay our respects to the people, the cultures and the elders past and present. And here in Canberra, where we're giving this talk today, we are on Ngunnawal and Ngambri country. I extend that acknowledgement and respect to any Aboriginal and Torres Strait Islander people who are here today or listening online. I myself grew up on Ngarigo country, just to the south of here, in the Snowy Mountains. The Ngarigo people call themselves the Snow People, and I acknowledge that role that growing up on their country played in my life. So while I grew up on Snow People country, you'd think it'd be easy to get up on a cold morning, but I appreciate everyone's time here today and braving the Canberra winter. I'm so glad to see you all here this morning, and welcome again to today's Wednesday public seminar. Today we are joined by representatives from 3 national science agencies who are part of the Critical Minerals Research and Development Hub. We'll hear 3 presentations about how these organisations are working together to define practical pathways towards development of Australia's less well-defined and lower-grade rare earth deposits. So, first we have Dr. Karin Soldenhoff, who is employed at the Australian Nuclear Science and Technology Organisation, or ANSTO, as a principal consultant in the Minerals Business Unit, which she co-founded in 2004. In her current role, she provides oversight and broad technical direction for research and commercially sponsored projects in hydrometallurgical process development, with a special emphasis in advanced separation technologies such as ion exchange and solvent extraction. Next, we have Dr. Jessica Walsh, who is the project leader of the Accelerating Development of Australia's Rare Earth Resources, or ADARA, project here at Geoscience Australia, which operates under the funding envelope of the Australian Critical Minerals R&D Hub. This project is a collaboration between Geoscience Australia, CSIRO and ANSTO, with ANSTO as the lead partner. Next and finally, Dr. Mark Pearce is currently Research Director for CSIRO Minerals Resources Characterisation Program, a research program of 30 scientists who specialise in developing new techniques and instrumentation to analyse rocks and minerals. The scientists in Mark's program work with other CSIRO research groups to ensure CSIRO's research is based on high quality analyses and are constantly developing new techniques to analyse a range of critical minerals and strategic materials. So can we please all join me in welcoming them here today? That's Karin. Thank you.
Well, thank you very much for the introduction, Mr. Chair, and good morning to everyone who's here. It is a pleasure to be here and really with my colleagues it's a little bit of a different type of approach. Minerals generally does a lot of business, and so it's nice to be able to work with my colleagues across the science agencies. Now, just to get started, the structure of this talk, I thought I'd start broad and actually introduce the topic of rare earths. Why is there a sudden interest in rare earths? And also provide you some background about what Australia is actually doing in this area. And then follow that up by the introduction to the research project to give you the context of why we're even doing this project, what we think we are going to achieve with it, and what is the challenge that we're all trying to address. So first of all, a little bit about ANSTO. ANSTO stands for Australian Nuclear Science and Technology Organisation, and this is where I work with. It is not often associated with minerals. Essentially, we have 2 sites. One is the Lucas Heights in Sydney, and the other one is the Australian Synchrotron in Melbourne. So that's where we operate out of. Now, ANSTO is better known for the operation of the only nuclear reactor in Australia. It's a research reactor that also acts as a radiopharmaceutical manufacturing facility. ANSTO also operates a range of advanced scientific infrastructure for the research community. But perhaps what's less well known is that we operate a number of business units, and one of them is minerals. And so we work very closely with industry, and we get most of our funding from industry. So coming back to the rare earths. The rare earths are a set of elements, there's about 15 of them, also known as the lanthanides. They can be found at the bottom of the periodic table. And, you know, they've kind of had a very subdued existence where people didn't take very much notice of them in terms of the general public. But very recently, you know, it's become a very common word in the vocabulary of many politicians. And we kind of hear of all sorts of things happening because of the interest of geopolitical interest in rare earths. Anyway, but they generally, one thing to remember about them is they occur together. So you cannot find one of them particularly in a deposit. They generally are associated with each other and in various proportions. So the rare earths go from lanthanum to lutetium. Often yttrium is also included in that group. So why are people interested in rare earths? Well, first of all, let's look at the set of them. Generally, we tend to talk about rare earths they fall into two major groups. The light rare earths, comprising of lanthanum, cerium, praseodymium, and neodymium. And then the others, we kind of bunched them into a very broad category of heavy rare earths. And why are they of interest? They're of interest because they tend to have very special properties, be it magnetic, optical, and otherwise, that actually means that they have applicability in a very wide range of areas, which means that you can't think of modern life without it. But they are not needed in very high quantities. They're often kind of known as the salt and pepper elements, where you can sprinkle them out in applications and give for particular purposes, but you know, they're not necessarily always the major players. So if we think about applications in general, if we start with the light rare earths, lanthanum and cerium, you can find them in rechargeable batteries, and then in tablets and smartphones, in the screens of tablets and smartphones, in catalytic converters for ICE vehicles. Looking now at the praseodymium neodymium, which is still part of the light rare earths, have applicability in permanent magnets, wind turbines, electric cars, that sort of thing. Also in MRI machines. And then there's gadolinium and lutetium that's used in PET imaging, terbium and yttrium that's used in fiber optics, yttrium as well used in fluorescent bulbs, and you know, a whole range and gamut of electronics. So as you can see, they've got a very wide application. But particularly of importance are praseodymium and neodymium, terbium and dysprosium, and they tend to be known as the magnet rare earths. And the reason for them is because those four elements are required to manufacture permanent magnets. And they are important components for our energy transition. So, you know, they're applied in wind turbines and in the manufacture of electric vehicles. These four elements alone are the ones that actually drive the demand. So the extra demand for rare earths at the present time is coming from the demand for these four elements. Now, where can you find them? I think it's often said that the rare earths are actually not rare. You can find them in a very wide range of geological settings. There's about 150 or even above types of minerals that contain rare earths. So they're available in a wide range of settings, like I mentioned. But there's particularly 4 minerals that have, in the past, been exploited economically, and so those are the ones that are quite important. First up, we start with the light rare earths in the monazite group. These are rare earth phosphates, and they tend to be found in heavy mineral sands and some other hard rock deposits. Also part of the exploited mineralogy is the bastnasite, found in Mountain Pass in California. There's a big deposit there that historically has been exploited and recently is also started producing again. Now, one thing you'll find in this light rare earth group, that if you look at the composition, half of it is cerium. And, there's a big contribution from lanthanum as well. So if you're after the sort of magnet rare earths, the neodymium and praseodymium, you've got the challenge of having to deal with lanthanum and cerium that come along with it. Now, that exemplifies some of the challenges that a metallurgist has, in that you might be wanting a certain thing, but you get everything together. When it comes to the heavy rare earths, it's a similar type of situation. You can find heavies, or in this case, the stuff that you want, that you're looking for, the terbium and dysprosium, in xenotime. Now, xenotime can occur associated with monazite, but it's much less common. And then, of course, there's the ionic clays, which, to a large extent and historically, have been mainly mined and exploited in China. But that situation is changing quite rapidly. In this case, if you look at the heavy rare earths as well, you'll notice that the most of the highest mass, or most of it, is comprised of yttrium. So we have a similar sort of challenge in that you have to separate the yttrium out if you're really looking after the terbium and dysprosium. So this graph here on the left gives you a bit of an idea of, again, this dichotomy between the mass composition and the value that you extract from these minerals. So we have a composite on the left-hand side. There's on the column graph there, you see the composition, the mass composition of monazite. You will notice that 70% of that mass comprises of the lanthanum and the cerium. But if you take that same composition and you look at the basket price, which is essentially looking at for how much you can actually sell all these elements for, you'll notice that the lanthanum and the cerium only provide 1% of the value. So this is a big challenge. Coming now, a similar sort of story for the heavy rare earths. You've got the mass composition. The main component is yttrium, 61% of the mass, 11% of the value. And on the other hand, the terbium and dysprosium is only 10% of the mass and 67% of the value. Now, when we look at, the things that we want, which are the manufactured products, that's what everybody's really looking for. And we think back about where all these things come from, we have to look at the whole supply chain. In other words, it starts off with mining. You mine the ore, and then you upgrade it, you beneficiate it, you extract the mineral concentrate in some shape or form, and those are generally known as the upstream processes. Now, Australia is very well versed in those kind of technologies. We do very well in that area. But once you've actually got a mineral concentrate, what you need to do then is attack it in some way to destroy the matrix. If you've got a rare earth phosphate matrix, and that generally needs higher temperatures and more aggressive conditions. And so what we're doing now is something different from mining. It's actually a metallurgical process where you have, often you attack it either with a strong alkali or an acid. You tend to dissolve a lot of the stuff that you want, but also the stuff that you don't want that comes along for the ride with the gangue minerals. And so you'll end up with solutions that comprise of a gambit. You've got all of the rare earths in there to start with, and then you've got a suite of impurities that you've got to deal with. And so in the extractive metallurgy part of the supply chain, what you're doing is you're removing the impurities that are non-rare earths, and at the end, you'll end up with a mixed chemical rare earth concentrate, which is now, pretty pure in terms of rare earths, but they're all mixed together in the compositions from that were essentially available in the ore. Now, the next process up is the separation. So you've now got to separate that particular mixed intermediate into the individual rare earths. And then after that, you've got to reduce it into a metal and then alloy it and make specific alloys that will actually feed the manufacturing specifications. And the manufacturing specifications, if you look at the number of applications, are very wide. And so that becomes a very specialized area as well. So looking first at the mining and who is doing the mining, if we look at the total global mining output, it's of the order of 400,000 tons a year. And that is a very small amount, because if we compare it with iron ore, for instance, or coal, I mean, we're talking about an export industry in Australia alone, which is of the order of 800 to 2,000 times the size of the tonnages we're talking about. So global demand, in terms of tonnages, is very, very low. And who is actually doing that mining? Well, obviously, China dominates. Then we've got the United States, because that's the contribution from the Mountain Pass site, followed by Myanmar, which I'll talk about a little bit later on as well. And then Australia is in fourth position, and with close billing from Nigeria and Thailand. Now, if we look at it another way and look at the supply chain in terms of who's active in which area, we're starting off, first of all, with the mining, which we've just spoken about. And yes, China dominates, but there's a few other players that are also coming into play. But then we move one step up the supply chain, and we look at the rare earth oxides, who's processing, who's separating them, not only doing the metallurgy, but also separating into individual products. And you see that China, once again, dominates. And there's a little sliver there of Malaysia, and that represents essentially the activities of an Australian mining company by the name of Lynas that takes concentrates from Western Australia and then processes them in Malaysia. Moving then on to the metals, the story is pretty much the same, except that you now see Japan. Japan in there, and Japan is also present in the manufacture of the permanent magnets. And when you look at, for instance, at one example of the end product, which is the wind turbines, you might think that, okay, Europe is very active there, and that's good. But if they want to manufacture wind turbines, where are they going to get the permanent magnets from? Well, they have to get them essentially from China. On the other hand, if you're a new player or a newcomer somewhere else in the supply chain, whether it's mining or rare earth processing or whatnot, I mean, you've got very few choices about where you're going to place your product. So you can start to see that essentially the challenges with the supply chain are the fact that it's so concentrated, and for that reason, it poses a risk. And this risk is why a lot of different governments have actually declared that the rare earths are critical minerals. Not so much because the minerals are in short supply, but because the processing and essentially moving through all these different industries is challenging from a business point of view. Now, what is Australia doing? Well, Australia's been doing plenty. in here, I've actually shown a list of 9 projects that have been highlighted in the Austrade Critical Minerals Prospectus, and this was published in April 2025, so it's really very recent. So you've got Lynas in the middle there as an operating company, and then there's 8 other projects. In construction, there's Iluka that is now in construction with the support of a loan from the Australian government to actually not only process their stockpile of monazite, but also to provide some separation capability. You've got 2 other projects, Arafura and Hastings, that are pre-construction stage. And then all of those 4 projects actually are mainly light rare earth projects. So, they've got mainly neodymium and praseodymium. But on the eastern side of Australia, you've got projects that, although not classified as heavy rare earth projects, they've got a higher proportion of heavy rare earths, so that's good. And they're at the advanced stage of project development. And then finally, as an outlier, you've got Northern Minerals that it actually contains xenotime, and so that is definitely classified as a heavy rare earth. In fact, some of that sort of concentrate is going to be fed into Iluka for their separation plant. Now, Lynas is the only operating mine and the only operator of rare earths in Australia. They are the poster child for the success story of how they've managed to break into the market, essentially with a lot of support from the Japanese government. So they've got a mine that they exploit, the Mount Weld. They ship their concentrate to Malaysia, where they separate, and they've got a processing plant there. But very recently, they've also started operating a processing plant in Kalgoorlie, where they take their mineral concentrate and produce an intermediate chemical. They're also active. They've received some funding from the US to open up a separation plant in the States. Now, of all the other projects, or all the 8 projects, ANSO has actually been supported the project development of 6 of the other projects that I've outlined in the previous slides. And we did the process development work and also the piloting. So we've been very active in this extractive metallurgy area, and a lot of the processing that we've tested involved acid baking and then impurity removal, and then producing a mixed rare earth carbonate, which is shown in the picture there. But then after, like I mentioned before, after you produce that intermediate, you now need to separate it. And you have to separate it not just roughly, but into high purity products, ranging from 2 nines to 4 nines. Now, in terms of 4 nines, what do we mean by 4 nines? It means that you have to have a product which is 99.99% pure. And what that actually means is that out of all of the rare earths, which, as we know, happen together, if you want a purity of 99.99, it means that 100 parts per million is the maximum allowed of all the other rare earths together. So it's quite it's quite a big challenge. And the reason why it's a big challenge is that in nature, their chemistries are very, very similar. So whatever you do to one, you tend to do to others. And so how do you actually separate them from each other? Well, the only, at the moment, practical way of doing it that's been exploited economically is by using of solvent extraction. Now, solvent extraction uses a solvent with a specific reagent in there that tends to have a very small propensity for one element over the other, but this is not a very high separation factor. To give you a bit of an idea of the challenge that is faced in such separations, and you can have a look at this is just a graph of percentage extraction into the organic solvent with pH, and you can see that if you look at, for instance, the separation of praseodymium, neodymium, they're nearly on top of each other. It means the separation factors are very, very low. So if we think about solvent extraction is used, for instance, in separating cobalt and nickel, and the separation factors there are in the thousands. But if you look at the separation factor for praseodymium and neodymium, it's below 2. And if we think about a separation factor of 1 as being impossible to separate physically, then you start to understand the type of challenge that we face. And so what happens, you can use this technology, but it does mean that you need a lot of different stages in order to effect the separations that you want. You need to slice and dice and develop the skills to do that. If you want a whole refinery to separate all of the 15 rare earths, you need a refinery that contains different circuits, maybe 15, maybe 16, containing up to 1,000 stages. So there is complexity in that technology. ANSTO has actually been working in this area for now 30 years. We started off with liners in the 1990s, and so we've developed the skill set. I think we've caught up with the technology, and in fact, we've helped some of these projects achieve the demonstration and the production of some samples. On the left-hand side there is the production of NdPr for Arafura, where we achieved 3 nines purity, and that was in 2020. In 2023, we demonstrated for the Australian Strategic Mineral Materials, ASM, the production of 4 nines terbium and 3 nines dysprosium. Now, this was the first in Australia, and this technology is very well guarded and kept confidential by the companies that actually use it. So that was quite an achievement. Now, the other thing that I wanted to turn to your attention was the fact that one of the projects, ASM, that exploits the Trinity Double deposit, they have actually gone one step further and actually established a metallization plant. They've done so in Korea, and the reason for that is because Korea is close to a manufacturing hub. So they are attacking this problem of the supply chain from both ends. They've got the double deposits, and they've spent 16 years developing the process flow sheet for that. But at the same time, they've also basically now built a plant which is in production in South Korea, and to metallize and attack it from that end. Now, that brings us to the project that we are undertaking under the auspices of the Critical Minerals R&D Hub. And the objective of this project is still in rare earths, but I think I've skipped. Yes, the objective of this project is essentially to target lower grade deposits. And we have got plenty of those around the country. But they are at the very early stages of development, so it's difficult to know whether they're going to be economic and essentially which processes are really appropriate for them. And the reason why we're even interested in these deposits is because they tend to be rich in terbium and dysprosium. But it is definitely critical to establish the economic potential of these deposits, and this is the main subject area for this research. Now, to give you a little bit of context, if we think about the production or who manufactures the terbium and dysprosium at the moment, and there's nowhere else but in China. So when we looked at that supply chain where we saw that Lynas was producing some of the separated light rare earths, it's only the light rare earths. So in terms of the heavies, essentially the Chinese have an absolute monopoly. So if you want permanent magnets, where is the terbium and dysprosium coming from? Now, the Chinese have historically exploited the ionic clays. The ionic clays in southern China are a little bit different from the hard rock deposits that I've been talking about. And the reason for that is because the rare earths tend to be very loosely held, and so it's easy. You can actually attack them with very mild sort of chemical reagents. And so they are kind of vulnerable to be exploited by informal mining. And in fact, the Chinese have suffered from some adverse sort of environmental impacts, and they've been cracking down quite hard on their own industries. But unfortunately, what's happened is that the industry has basically jumped ship, and there's been a lot of activity just on the borders with China in Myanmar. And if we think about it, if we remember, Myanmar is now the third producer of rare earths, and in this case, it's only heavy rare earths. And where all of the activity happens, it's in unregulated mining activities, which is causing quite a lot of damage. And this has been accelerated to a large extent. If we look at the satellite mining maps of in 2021, the Chinese border is here in light gray, and this is the Myanmar border. And so all of these yellow sort of dots represent informal settlements where people basically just inject ammonium nitrate into the landscape, and then they collect the liquor at the bottom, throw a bit of oxalic acid, and you've got your heavy rare earth chemical concentrate. So it is a little bit of, I guess, an irony that whilst we are looking at this green transition that requires these rare earth elements, but where are these particular two coming from? Well, they're coming from these areas. So I think the export of heavy rare earth chemical concentrates from Myanmar to China last year was about 40,000 tons, and considering that the total global markets, including all of that lanthanum and cerium, is 400, you start seeing the scope of the challenge. So what are we doing about it? Well, we are going to find an alternative way, environmentally friendly, an economic way of trying to process these low-grade ionic clays and clay-hosted rare earth deposits. So this project has been structured in a way that Australian is the lead agency. We have got contributions from Geoscience Australia and CSIRO in the geology and mineralogy. ANSTO is looking after the process development and looking at economic ways of dealing with these challenges. And the other thing that we're also doing is upgrading our facilities so that it will allow us to use or to be able to cope with much higher tonnages, because obviously when you have a very low grade sort of starting material, it means that you've got to kind of process a lot more tons in order to actually get to the outcome. So that's the end of my talk, and so I would like now to invite Jessica Walsh from Geoscience Australia to carry on.
Fabulous. Thank you so much, Karin, for a really in-depth and interesting overview of rare earth elements, the state of play kind of globally, but also the situation that we have here in Australia as well. So just a little bit more on the Critical Minerals Research and Development Hub. So I know we're here for the public talk. However, outside of this public talk, we're actually having like a little bit of a conference which has the three science agencies, ANSTO, CSIRO and Geoscience Australia. And we're looking at kind of critical minerals in general and what that means for, say, supply chains. And then, we're looking at, say, deposits at a national scale, down to, what we see at, then deposit scale and then processing as well. So there's a whole lot of different kind of projects that fall under the envelope. But again, we're today speaking about this accelerated rare earths development project, or the ADERA project. So I guess, what is Geoscience Australia's contribution? So the aim of at least Geoscience Australia's input is to, of course, increase knowledge of Australia's rare earth mineral systems. And then that also includes expanding geological understanding of their potential and improve, of course, investment confidence for new exploration and discovery within Australia. And so again, as Karin kind of alluded to, what we're really focusing on for this project is clay-hosted rare earth elements deposits. So we're really kind of looking into the regolith and what that means for rare earth elements to be hosted there, whether this means in mineral form or ion adsorption. But what we're trying to do at GA is understand the entire, the mineral system itself. So there's a lot of challenges with rare earths in general, but for us, there's actually no mineral systems model that actually exists for clay-hosted rare earth element deposit formation. And as Karin alluded to as well, global examples are often used as analogues for the Australian systems. And of course, there may be bits and pieces that we can kind of take from that, but that doesn't actually mean that we can use these as direct replications for how we understand the deposits here. So our contribution will be the National Scale Mineral Potential Assessment. So I guess, because this is a public talk, let's all bring this back a little bit before we get on to how we actually do mineral potential modelling here at Geoscience Australia. So of course, what is a mineral system? This is built off a really early definition in the mid-1990s. So Wyborn, I guess, was, a lot of the work here is kind of built off the foundation of her work. And then so a mineral system as defined in the mid-90s is all the geological factors that actually control the generation and of course then the preservation of these deposits. And there's a stress on the processes that are actually involved in mobilising the ore components from a source and then transporting and accumulating these in a more concentrated form. And then of course preserving them throughout subsequent geological history. So we've taken that and kind of adapted it into something that's a little bit more, I guess, streamlined here at Geoscience Australia. So mineral systems are defined as all geological processes that control the generation and the preservation of mineral deposits at the global, then to deposit scale. And these are actually modelled using components, or what we define as components. So modelling using a mineral systems framework, this actually incorporates 5 different components that I'll run through just now. So I introduce you to the mineral systems framework, and this is used to, I guess, understand holistically, a particular type of mineral system. So this is what we're actually employing to begin to understand the clay-hosted rare earth element mineral systems here in the Australian context. So one thing that I will point to as well is that this type of framework, incorporates everything from geological time from very, very long ago to the near present, and also spans, across an enormous scale from craton all the way down to the micro scale. So the first part of the framework is then understanding the source of the metals, fluids and ligands. So where were the original source of the rare earths? What were the, rock types that we should be interested in? Were these elevated in rare earths? And how much does that actually matter? Are there multiple contributing sources? So 2 is the energy sources and fluid flow drivers. That's kind of in this yellow part just down in here. So I guess when it comes to regular systems, we then begin to think of, what type of energy sources can we think produce or break down or weather these different rock forms. So 3, for the mineral systems framework, we have lithological architecture and fluid flow pathways. And that's this orange section in here. So I guess in a maybe more traditional sense, like lithological architecture, we might think of, say, magmas coming up from the base. But in, say, a regular system, this is more, the type of thing where we could be thinking of fluid leaching actually down profiles as well. So I guess there's a need to, begin to understand, yes, we may understand, hard rock systems, but then we also need to incorporate all of our knowledge around regular systems as well and build that into our understanding of a mineral systems framework. Number 4, this, green section in here is ore deposition and gradient. So where is the ore deposited and why? And then, of course, number 5, the grey section that kind of envelopes the top, is preservation in and of itself. It's all fabulous that we can have, these wonderful mineral systems, clay-hosted systems, but if we can't actually preserve these to the current day, and even furthermore, have these, say, at surface or near surface for economic extraction, then I guess, you can understand the mineral system as much as you want, but if it's gone, it's gone. So now we've kind of gone through a little bit of an understanding of mineral systems as a concept And now, how do we actually create a mineral potential model? So again, this is understanding the processes that then form these mineral systems, these clay-hosted systems, and then understanding what processes can actually be mapped. And can these be mapped then, say, at a national scale, which is kind of like the bread and butter of what we do here at Geoscience Australia. So the mineral potential models represent the geological potential of an area to host a specific ore deposit, or in this sense, a clay-hosted deposit. So of course it's generated from the synthesis of available both knowledge and data. Sometimes we have a lot of knowledge, but we don't have the appropriate data, and vice versa. Sometimes less of either, and that's not so great. Yes, and then, at the end of the day, the mineral potential model is then, translating mineral systems processes into mappable criteria. So you can see, what we have here is an assessment criteria table. So this is kind of, the backbone of how we begin to produce these models. So I do apologise, this is in draft mode at the moment. So I can't actually go into a lot of the fundamental details, but we will be releasing all of this data at the end of the project. So the Tranche 1 project for Adera, the rare earths project, will finish in March 2026. But this is, I guess, like the systematics and the methodology for how we produce these particular mineral potential models. So more on mineral potential models. So GIS is actually used to generate the input maps for each of these components. So again, these components or input data sets are over in here, and the mineral system components are, say, those sources, energy, architecture, ore deposition, and of course, preservation. So the model actually combines and weighs these input maps. And then relative prospectivity is indicated using, say, a cold to hot colour scheme, which you can kind of see from the diagram here. So this is an example taken from Skero et al. 2019 on the IOCG mineral potential model. So overall, what the model is actually aiming to do is map where important processes overlap. So that's what you can see inside of kind of those hotter colours there. And that's going to suggest more favourable mineralisation kind of conditions. And the entire aim of this is then to actually reduce that search space. And this could be for industry, but it can also be for our colleagues in the surveys as well. And of course, the input maps and model need to be geologically reasonable, statistically valid, and also fit for purpose as well. So for the models, a hybrid knowledge and data-driven weighted index or index overlay approach is what's actually used. So this is based on the synthesis, again, of really large volumes of pre-competitive data with mineral systems expertise. So it's a multi-step process where individual mappable criteria are used. It's integrated to produce those 5 component maps, and then it's integrated to produce then that end product, the mineral potential map itself. So data coverage maps can be produced to indicate where areas have high amounts of missing data or information, and each actual mineral system needs to be modelled individually as well. So I've got a little video here, so hopefully, no. That was almost there. Is it working? Bother. I did try this beforehand, it doesn't seem to have worked. But you get that on the big jobs. So however, the aim of the slide, which is really great because it seems to have kind of finished on like the end part, but what it goes to show is that there are multiple, data sets that go into understanding these individual components, which are then overlaid together to produce a mineral potential map in and of itself. So this is the aim for the clay-hosted deposits, and this is an example by Ford et al. Of the carbonatite-related rare earths mineral potential map. So then mineral potential models. So again, the idea is to synthesise large volumes of pre-competitive data with mineral systems expertise and knowledge. It's then aiming to translate these mineral system processes into actual mappable criteria. It evaluates the predictive power of individual data sets and overall mineral potential map. And then data coverage maps are used to indicate where areas have high amounts of missing data or information. And I guess what Karin kind of alluded to earlier as well is that ANSTO and CSIRO and Geoscience Australia have all been, I guess, working in the rare earth space kind of before this project, and we'll also continue to work on this kind of after this project as well with, and I think the Critical Minerals Research and Development Hub have done a really fabulous job of kind of bringing our agencies together and really trying to understand the intricacies at each of the different levels, whether it's understanding at a national scale, going down to deposit scale, and then the processing and what that means afterwards as well. So for Geoscience Australia, we have what's named the Resourcing Australia's Prosperity Initiative, which is a $3.4 billion 35-year landmark kind of initiative that's going to be led by us. But what I want to take from here is that, we're going to be, furthering our Australia-wide geoscience data and then using this to build national resource assessments as well, all these mineral potential maps. So when it comes to national resource assessments as well, moving forward, it's not just going to incorporate, say, rare earth element mineral potential maps, but it's also going to look into things such as economic fairways, and identifying even, say, green metal opportunities and costs as well. And again, the Australian-wide geoscience data spans fields of geology, geochemistry and geophysics, which is all what we'll be building on for the future as well under Resourcing Australia's Prosperity Initiative. So understanding things, understanding mineral systems at a national scale is one thing, which is very important, and understanding those processes. However, taking that and then applying that knowledge and really digging in deep is something that our friends at CSIRO have been doing, and they do it really well. So I'll now pass over to Mark Pearce from CSIRO to speak to us about your work.
Thanks, Jess. So CSIRO's role in this project is to work at the deposit to camp scale, so a slightly larger area containing potentially multiple deposits, to really understand and hopefully produce some of those geologically reasonable models that Jess was talking about for how these deposits form, and look at increasingly smaller scales at the deposit mineralogy, because mineralogy in mineral processing and extracting these deposits is always the king. It will control what you can and can't do. And to kind of bridge that link between the exploration and into the mineral processing. So as has kind of been alluded to, not all clay-hosted deposits are created equally. Karin has mentioned ion absorption deposits. We variously mentioned clay-hosted rare earth deposits. And so I thought I'd just point out here these kind of two parts of this clay-hosted system that we're talking about. So one is the clay minerals. These are sheety minerals. And the ion absorption deposits are where the ions, so we have the rare earth elements themselves here, they're kind of loosely bound to the outside of these clay minerals. And so they're easy to extract with relatively benign chemicals like the stuff that Karin was talking about. And we also have, in some of these deposits, residual phases that contain the rare earths. So in the production of these deposits, we're actually weathering the rocks that the original rare earths occur in. And we can have leftover bits of the minerals that occur in the rocks below that host the rare earths. And so these are much more tightly bound and much more challenging to extract. And so these residual bits occur in very clay-rich rocks, so can often look like the ion absorption deposits, but present a much different processing challenge. And so understanding whether we have these residual minerals that are left over during the weathering process, or whether we have these nice ion absorption deposits, how we get these, where we get these, and what's the distribution and why is kind of what we're looking at in this part of the project. And we're, to tackle this, we're bringing together a number of different elements that CSIRO has particular specialities in. So the first one is regolith geoscience, and Jess mentioned the regolith. This is the layer of weathered rock that covers a lot of Australia. When you go out into the outback, you often don't get the nice solid bedrock, you get weathered material. And from our point of view, this is both a challenge, but it's also an opportunity, because the weathered material is the stuff that hosts some of these deposits. And this is based on some of this model here is based on some of the work that CSIRO researchers have done in the past. And it's a kind of working model that we took into this project to test whether it works much more widely across Australia. And the regolith kind of consists of two key components. One is the saprolite or in situ regolith, which is material that is composed of the rock that's left over during the weathering process, but is largely derived from the stuff underneath, so it hasn't moved anywhere. And then we have the transported material over the top, which is stuff that's been transported in by things like channels that develop on the top. And so we're looking at where in this system between the in situ and transported material these rare earths occur. And the deposits we've looked at previously, a lot of these rare earths occur in the in situ material. So there's these leftover phases and slightly changed phases that were once present in the basement rocks, but are now containing our rare earths. And they pose quite a challenge in terms of the processing. We're also pulling in geophysics, so this is some of the nice AusAEM data that Geoscience Australia have collected and curated, and we're using that data, processing it a bit further, and combining it to extend our knowledge that we can get from drill core into 3 dimensions, because this geophysics is very good at showing us what's happening in the subsurface, but also in 3 dimensions. And so this figure here just shows variability in the electromagnetic properties of the subsurface correlated with the rare earth contents across one of these deposits. And you can see this kind of reddy-orange zone in the middle that has specific geophysical properties is also the zone that contains the rare earths. So we think there's potential for mapping these things out in terms of the distribution of them using these nice geophysical data sets. The final piece of the puzzle from our point of view is the really detailed mineralogy. And to understand clay-hosted deposits and other mineralogy, we're using a variety of techniques, one of them being X-ray diffraction. And so these rather complex-looking diagrams here show you a series of treatments of the clay material, much of which occurs in this very, very fine fraction, the less than 0.2 micrometer fraction. And as we distill down the sample, we concentrate the clay material, and using the techniques that we've developed over a number of decades, we're able to tell very precisely what the types of clays are. And we're also able to look at whether the rare earth bearing phases actually are concentrated in this fine material, or if we get rid of them as we refine down the material. So this gives us important information about potential hosts for our rare earths. Are they those nice, easily extractable clay absorption deposits, or are we looking at these residual phases? So we've been looking at a number of sites around Australia. The first one is down in the southwest of Western Australia, and this kind of builds on that model that I showed. It's the kind of next door area. We're testing whether the understanding that we have from work we've done actually extends within the same kind of geological domain. The second area is in South Australia, and this is kind of part of the same large basin, but it's actually looking at slightly different geology. So does our existing knowledge and understanding translate to similar but slightly different geology? And then the third example is in the Northern Territory, and this is much more different geology again, and further away. So can we generalize further this understanding that we have? How well does our current understanding kind of translate to these different deposits? And or do we need completely new understanding that would inform, for example, the work that GA is doing? So I've just got a few highlights from some of the case studies that we've done so far. So this is the Western Australia one, where the teams have been out into the field. They've looked at the surface to understand the different components of that regolith system, and they've started looking at this geophysical data that exists. And they've also been, for all three of these case studies, we're supported by the companies who are exploring in these areas, and they've provided us with drill core samples. And these are the kinds of data sets that we're generating. So this shows a whole range of different types of mineralogy. So we're looking in detail at how the minerals occur through the depth section. So this is a section going down one of these drill core profiles. And you can see relatively sharp changes in the colours, showing sharp changes in what minerals are present, and we're able to map out the different parts of that model. You can see about a third of the way down here, we've got this black layer, and the team have identified that this is a substantial layer containing organic material that actually marks the boundary between this in situ and transported material. And so it's quite important for letting us know where we are within the system. And you can also see over here, this purple column here is actually the total rare earth content. And so you can see most of the rare earths sit beneath this black layer which marks this boundary. And so it's telling us that these are within the residual material, and actually that correlates with what we're seeing from the rare earths being a bit more difficult to extract. They're locked up in some of these phases. This is initial work from the South Australian side, the South Australian case study, and this is based on data provided by the company who are supporting us there. And it's a very similar system. So the colours here on these vertical profiles are showing us the total rare earth content. And actually, you'll notice here that we've got some really juicy numbers, so upwards of 2,000 parts per million, sitting in this the bottom of this section, and that's actually this in situ material. However, the area that this particular company are targeting are this material in this kind of channel-like structure, and this is one of these channels that sits in the transported material. So in here, the grades aren't so high, but they're hopeful that this is more adsorbed material that's much more easy to extract. So we've got this trade-off between the really high grades, but also the ease of extraction. So in terms of this part of the project, what have we learned so far? Rare earths in the in situ regolith can often be difficult to extract, although we are testing that through a number of different examples. And the transported material can often be attractive, especially if we've got clays in some of these channels. And the accurate mapping out of these systems is very important for us to understand how they develop and the potential impacts on the processing. So to sum up the whole project, which is kind of nice interaction between the three science agencies, we're looking to find economic pathways for exploring and processing these relatively low-grade ionic or clay-hosted rare earth deposits. And we're kind of bringing together bits of what everybody does very well to do that, to understand the geology, the mineralogy, and then hopefully scale up processing and boost Australian rare earth industry. Thank you very much.
Thanks very much, Mark. And thanks again to all three of our presenters here, Mark, Jess and Karin. It was fantastic to see. I certainly learned a lot about rare earths, so it's fantastic. Look, we are right at time, unfortunately I don't think we're going to have time to ask any questions. So if you could all join me in thanking our presenters again, that would be fantastic.